Welcome to a new lecture on the binomial theorem. In this lecture, we will look at certain divisibility results which can be derived based on the binomial theorem. So once again, recall the binomial theorem is given by x plus y the whole power n equals summation r equal to 0 to n cr x power n minus r y power r, where we use cr to denote ncr. So to give you a flavor of the kind of results we'll be looking at today, let's look at the first example, which asks you to show that 3 power 2n plus 2 minus 8n minus 9 is divisible by 64 when n is a natural number. So it asks you to show that this term is divisible by 64 for natural numbers n. So at first sight, there doesn't seem to be a binomial expansion you can apply to generate this result. So we would like to create a binomial expansion to derive this result. And so notice that you have an exponent here, but you also have some terms here, and these terms are in general not divisible by 64 for n being natural numbers. So you can plug in certain natural numbers, and you can see that this term which is being subtracted from 3 power 2n plus 2 is not going to be divisible by 64. And so we would like to somehow get rid of these terms and leave the remaining term to be divisible by 64. So let's look at a way of re-expressing this term. So 3 power 2n plus 2 minus 8n minus 9 can be written as 9 power n plus 1, where I've just taken a power of 2 into 3 and written 3 square as 9, and you still have minus 8n minus 9. So now this looks a little more promising, because you have 9 power n plus 1, and you have a 9, and you have an 8n. So you can get rid of the 8n potentially by writing 9 as 1 plus 8. Erase this power n plus 1, and you have 8n minus 9. So this looks a little more promising. And now you have a term which you can expand using the binomial theorem. So let's try and expand this term. So this is nothing but n plus 1 c0 times 1 power n plus 1 plus n plus 1 c1 times 1 power n times 8 plus n plus 1 c2 1 power n minus 1 8 square, and so on. So we'll be concerned about the higher order terms later, and we're still subtracting 8n and 9 from this term. So let's see how this simplifies to. So this is nothing but the first term is 1. The second term is n plus 1 times 1 times 8. And the remaining terms can be succinctly written as summation r equal to 2 to n plus 1 cr 1 power n plus 1 minus r and 8 power r. And you still have to subtract 8n and 9 from this expression. So this looks a little more promising, because notice that these first two terms add up to exactly 8n plus 9, and so you can cancel these two terms, and so you're just left with summation r equal to 2 to n plus 1 cr 1 power n plus 1 minus r is just 1, and you have 8 power r. So this is what we're left with, and we want to show that this is divisible by 64. So notice that the summation runs from r equal to 2. So let's rewrite this as summation r equal to 0 to n minus 1 n plus 1 c r plus 2 8 power r plus 2. So we've just used a change of indices to rewrite this summation. And notice that there's an 8 power 2 here. You can pull that out. This is going to be 64 times summation r equal to 0 to n minus 1, n plus 1c r plus 2, 8 power r. So you have a 64 here, and you wanted to show that this term is divisible by 64, so that is good. So what we have to show is that this term is an integer. So that's all is that remains. So that term is clearly an integer because you have a summation of several terms where each term is made up of two integers themselves. So 8 power r is an integer, and n plus 1c r plus 2 again is an integer. So we have summation of integers, and so this term is an integer. So we have that this overall term is divisible by 64, which is the desired result. So we've seen an application of the binomial theorem where we somehow re-expressed our given term in terms of an expression from where we could use the binomial expansion and derive a divisibility result for the original term. So let's look at a second example. This example asks to show that 2 power 4n minus 2 power n times 7n plus 1 is divisible by 196 whenever n is a natural number. So this example is very similar to the previous one, and once again we have to figure out how to rewrite this original term in a form which is amenable to the binomial expansion. So notice now that we want to show that this term is divisible by 196, and 196 is nothing but 14 square, and you have a 7 here and a 2 power n here, so that looks promising. So let's see what we can do. So 2 power 4n minus 2 power n times 7n plus 1 can be rewritten as 16 power n minus 2 power n times 7n plus 1, where we just rewritten 2 power 4n as 16 power n. So now 16 can somehow be split into 14 and 2. So we can rewrite this as 2 plus 14 power n minus 2 power n times 7n plus 1. So this looks promising because now we have a 14 appear in a binomial term, and we want to show that this whole term is divisible by 196, which is 14 squared. So let's go through the motions again and use the binomial theorem to show that this is nothing but nc0, 2 power n, 14 power 0, plus nc1, 2 power n minus 1, 14 power 1, plus, let's rewrite the higher order terms as summation r equal to 2 to n, ncr, 2 power n minus r, 14 power r. And we subtract the original 2 power n times 7n plus 1 from this expansion. So once again, you can rewrite this as 2 power n plus n times 2 power n minus 1 times 14 plus summation r equal to 2 to n, ncr, 2 power n minus r, 14 power r. And you still have to subtract 2 power n times 7n plus 1. So this is nothing but 2 power n plus n times 2 power n times 7, where I've factorized 14 as 2 times 7, and you have a resulting summation r equal to 2 to n, ncr, 2 power n minus r, 14 power r, and you subtract 2 power n times 7n and a 2 power n, where I just expanded this term. So notice once again that you can cancel the first two terms with the terms being subtracted, and you're only left with this summation r equal to 2 to n, ncr 2 power n minus r, 14 power r. Now the arguments are quite similar to the previous one, previous example we've seen, so I won't go through this in detail. You can just rewrite this as 14 square times summation r equal to 0 to n minus 2 ncr plus 2 2 power n minus r minus 2 and 14 power where here you started with 2 power n minus 2, and so you're starting with 2 power n minus 2 again, and here you started with 14 square, and here you start with 14 power 0 since I pulled out a 14 square here. So this is what we are left with, and notice that this summation again is an integer, and we have this summation being multiplied by 14 square, which is 196, which is again an integer, and we wanted to show that this term is divisible by 196. So that's exactly what we've shown, since we factorized it into a form where we have a leading coefficient of 14 square. And so we've once again shown that this term is divisible by 196 whenever n is a natural number. So let's look at a multiple choice question, which is based on this flavor of problems. So the question asks you to show, it asks you when 5 power 99 is divided by 13, the remainder is, so it asks you to compute the remainder when 5 power 99 is divided by 13, and the options are 8, 9, 10, and none of these. So this is a kind of problem where it's hard to eliminate the options without actually solving the problem, because you have none of these where so even if you determine that this remainder is going to be even or odd, you're not really sure which option it is, since there's none of these, and even if the remainder is odd, you can't just conclude that the answer is 9. So you would actually have to derive the result for this example. So let's see how you can rewrite 5 power 99 to obtain an amenable result. So to arrive at the solution, let's try computing some powers of 5 to see where that gets us. So 5 power 1 is 5, which is quite far from 13, so it's not really much you can do about it. 5 square is 25, which is close to a multiple of 13. 13 times 2 is 26. So this looks promising. But 5 power 99 is not a direct power of, not an integral power of 5 square. And so let's try this approach. Let's write 5 power 99 as 5 times 5 power 98. Okay. I've just factorized 5 power 99 into a more suitable form. And now I can write this as 5 times 5 power 5 square power 49. And since I know that 5 square is close to a multiple of 13, this is nothing but 5 times 26 minus 1 power 49. 26 is a multiple of 13. So the divisibility results are going to be fairly easy to derive. So this is nothing but 5 times, and now you use the binomial expansion of 26 minus 1 whole power 49. So let's see how we can write this. It's like 49 C 0 minus 1 power 49, 26 power 0. So I'm starting off with minus 1 power 49 and 26 power 0, since we're only concerned with the power of 26, which is 0, since all other terms are going to be divisible by 13. So and you have 49C1 minus 1 power 48, 26 power 1, plus so on. So this is going to be the expansion of 26 minus 1, the whole power 49, and you have a leading term which is phi in this expression. So notice that all of these higher powers, as I mentioned, are going to be divisible by 13, and so since we only care about the remainder that this term leaves when divided by 13, we don't really care about these terms which are exactly divisible by 13. So this is the only remaining term is going to give us the remainder when you divide 5 power 99 by 13. So let's see what that gives us. It's 5 times 49C0 is 1 times minus 1 power 49 is minus 1 times 26 power 0 is 1, and so this gives us minus 5. So the remainder when 5 power 99 is divided by 13 is minus 5. For those of you who aren't used to this kind of notation, this might seem a little strange that you get a negative remainder, but to just get a positive remainder, you just add a multiple of 13. Since we've ignored so many multiples of 13, you get a negative number, but if you add a multiple of 13, you get 8. So the remainder when 5 power 99 is divided by 13 is 8. For those of you who are familiar with modular arithmetic, you can notice that the approach we took is very similar to the approach you take when you do such kinds of problems in number theory, where you try to get at a power of 5 which is close to a multiple of 13, and you just used remainder arguments where you ignored terms which were multiples of 13, and so you're only left with one term since you only care about the remainder. So this is a sample of a problem which could appear in an exam type situation where you're asked to derive a result based on the divisibility of a term by a natural number using the binomial theorem. So that's it for this lecture. Hope you enjoyed watching this lecture, and in the next lectures we will look at some example problems based on the binomial theorem. I thank you for your attention and hope you can join us next time.